Hello, everyone. So last time we looked at the concepts of continuous random variables and how we can define PDF in that case to find the probabilities. So last time looked at continuous random variables. And we defined PDF, and the notation was f of x. And how did we use this PDF? Well, this PDF had the feature that if you want to find the probability that the random variable x is between two numbers a and b, we can integrate this function from a to b f of x dx. And in particular, we saw that probability that x is equal to some number a means integral a to a of this PDF function. And integral a to a of any function is always 0. So any individual probability is 0. So probability of x being exactly equal to any number is 0. But instead, probability that x is between two numbers can be non-zero and can be found with this integral. And we also looked at the concept of a CDF. So CDF is a capital Fx of t, means probability that x is less than equal to t. So we said that this can be defined either in discrete case or continuous case. But in the case of continuous case, we can write this as an integral. We can write it as integral minus infinity to t f of x dx. And we also looked at properties of PDF and some properties of CDF. So important properties of PDF was that, first of all, f of x should be non-negative, and f of x must be integrable. And the whole integral must be 1. Similar to the PMF function. PMF function in the case of discrete probability is non-negative. And well, we didn't have this condition because we didn't talk about integrals in that case. But instead of the whole integral being 1, we had the sum. We had like this condition, sum of p of k equals 1. And in the case of discrete case, we have sum. In the case of continuous case, this sum is replaced by integral. And properties of CDF. Like this capital F x of x function. So first of all, we saw that if x is a continuous random variable, then f of x or capital F of x is a continuous function. This one, we proved it last time. Proved last time. So we saw that the PDF, small f of x, does not have to be continuous. Even if the random variable is continuous, the PDF does not have to be continuous. But CDF has to be always continuous as long as we have a continuous random variable. So we saw some examples last time. For example, PDF could have been, for example, Cx if x between 1 to 2, if you remember, and 0 otherwise. So in that case, PDF was obviously discontinuous. But even in this case, CDF, when we calculated CDF turned out to be continuous. So if we have a continuous random variable, PDF may or may not be continuous, but CDF is always continuous if we have a continuous random variable. So this is one important property of CDF that we saw last time. Let's look at more properties. More properties for CDF. So one property, first property we said last time. So second property, limit capital F of t, let's say, as t goes to infinity is 1, and limit capital F of t as t goes to minus infinity is 0. This is an important property of CDF. And why is that? Well, because capital F of t, so proof, capital F of t is P of the probability that x is less than or equal to t. So we can say that limit t goes to infinity, F of t is limit t goes to infinity, probability that x is less than or equal to t. And probability that x is less than infinity will be 1, because x is a random variable whose output is some real number. So any real number will be ultimately less than infinity. So this will be 1. Similarly, any real number, if it calculate the limit as t goes to minus infinity, well, no real number, again, remember that outputs of x are real numbers, and no real number can be said that is less than minus infinity. So probability of this event will be the empty set, and probability of empty set will be 0. So this probability will be 0. So this is an important property of CDFs. Now the next property of CDF is that CDF, or capital F of t, is an increasing function and what do we mean by increasing function? Namely, if A is less than or equal to B, then we can say that F of A, capital F of A, is less than or equal to capital F of B. So this is the meaning of increasing function. Increasing function means as you increase the inputs, the outputs also increase. So as we increase the inputs from A to B, the output increases from F of A to F of B. And how can we prove this property? Proof. So we have A less than B. And what is the definition of capital F of A? Capital F of A means probability that X is less than or equal to A. And this will be less than or equal to probability that X is less than or equal to B. And why is that? Because look at the events here. We are calculating probability of X less than or equal to A here. Our event here is X less than or equal to A. And our event in this side of inequality is X less than or equal to B. But B is bigger than A. So this event here is a subset of this event. So let me call this one, let's say, inequality star. Let's write here justification or star is that, let's say, if t belongs to this event, x less than equal to a, so that means x of t is less than equal to a. Remember, this is an event. Event means it's a set, so it contains some elements. So if I take some element, let's say t inside this event, then that means x of t is less than equal to a. X of t is a real number. The outputs of random variable are all real numbers. X of t is a real number, which has to be less than equal to a. But we are also assuming that a is less than equal to b. So that means x of t is less than equal to b. X of t is less than equal to b. And that means t belongs to x less than equal to b. See, a is less than b. So for example, if a is 5 and b is 10, for example, if x is less than 5, then it will be automatically less than 10 as well. So if x is less than a is less than b, so x is less than b. And if x of t is less than b, that means t belongs to this event, x less than b. So look at here, I took an arbitrary element in this event, and I showed that that arbitrary element must be in this event as well. So this means that this event here is a subset of this event. Therefore, we can say that x less than equal to a is a subset of x less than equal to b. And this means that probability that x less than equal to a is less than equal to probability x less than equal to b. Remember that in the first chapter, using axioms of probability, we showed that if you have two events and one is a subset of another, probability of first event will be less than equal to probability of second event. So we proved this inequality star. And once we prove this, well, capital F of A is probability x less than equal to A less than this. And probability x less than equal to B is same as capital F of B. Please remember that capital F of t for any t was probability x less than t, less than equal to t. So probability x less than equal to b is same as capital F of b. So that means we showed that capital F of A is less than equal to capital F of B as desired. And this means our CDF function, capital F of T, is an increasing function. Increasing function. So this is another important property of CDFs. And another important property that we saw last time, that we mentioned one more time, was that if PDF, which means small f of x, is a continuous function, PDF is a continuous function, then CDF capital F of x is differentiable and derivative of capital F of x is small f of x. This one we also saw last time. Just reminding you again about this property, that this property, if you remember, originated from FTC part 1. Because this capital F is the same function that you called it area function in Math 114. And we know that the area function is differentiable and derivative of area function is the original function small f, as long as the original function is continuous. Yeah, so in Math 114, you wrote this as d to dx of, let's say, integral a to x, f of t dt equals f of x. So you call this function area function, and you verified that this function is differentiable, and derivative of this function is this original function small f, as long as this function inside this integrand is continuous. So again, we are in the same situation here. And instead of a to x, here we have minus infinity to x, which is our capital F of x. And therefore, we can say that this capital F is differentiable with derivative small f if small f is continuous. In Math 114, you call this area function. Here we are calling it CDF, or cumulative distributive function. So this is another important property of CDFs. Now let's look at an example. Let f of x equals, let's say, c e to power minus x for x bigger than equal to 0, 0 for x less than 0. Find the constant c such that f of x above becomes a PDF of a random variable So let's say this is part A. Part B, find CDF, which means capital F of x. And part C, let's say verify the properties of CDF. So first of all, we need to find the constant C. How do we find the constant C? Well, we have to look at the properties of PDF. Properties of PDF was saying that, first of all, it has to be non-negative, it has to be integrable, and the whole integral has to be 1. Well, here, f of x being bigger than or equal to 0 implies what? So for part A, note that f of x has to be bigger than or equal to 0. Well, 0 is bigger than or equal to 0, which we have it in the second piece of the function. And the first piece being bigger than or equal to 0 implies that c has to be bigger than or equal to 0, because this part is exponential and is bigger than or equal to 0 anyways. So that means c has to be bigger than or equal to 0. So c times e to power minus x has to be bigger than or equal to 0. And because the second term is always bigger than or equal to 0, that means c has to be bigger than or equal to 0. And f of x is integrable. Why is it integrable? We said that if you have a function which is bounded, in this case is bounded because 0 is bounded and this part is bounded as x goes to infinity, this goes to 0. So this function does not go to infinity or minus infinity in any case and remains bounded. So if a function is bounded and has finitely many discontinuities, well, this piece is continuous, this piece is also continuous, and it has only one discontinuity at 0. If C turns out to be non-zero, well, the right limit at this point will be non-zero, and left limit is 0. So we'll have one discontinuity at 0. But we said that if you have a bounded function with finitely many discontinuities, then that function is integrable. So this function is integrable. So this condition is satisfied. And the last condition that I have to check whether it's true or not is whether the whole integral is 1. So how much is the whole integral? And f of x is integrable, and need to check whether integral minus infinity to infinity f of x dx is 1. So this one, the integral minus infinity to infinity f of x dx. Let's look at the formula for f of x. Before 0, the function is 0, and the integral will be 0. So I can break down this integral as integral minus infinity to 0 f of x dx, and then integral 0 to infinity f of x dx. Minus infinity to 0, the function is 0. And then 0 to infinity, the function is c times e to power minus x dx. And this has to be 1. Well, this function is this integral is 0. And then I need to calculate this integral, which means I need to find an antiderivative of e to power minus x. Antiderivative of e to power minus x is minus e to power minus x. Then I need to take the limit to infinity from 0 to t. Because we know that when we have integral a to infinity, means like a to t, where t goes to infinity. So I can replace this with 0 to t, t goes to infinity. And then I need antiderivative of e to power minus x, which is minus e to power minus x. And I need to calculate it between 0 to t. So then this will be same as c times minus e to power minus infinity minus 1. This function at 0 is e to power 0, which is 1. So this will be minus 1 and minus 1. E to power minus infinity, we know it's 0. So then this is same as c times 0 plus 1, which is c. So we can say that, well, the first term was 0. Second term turns out to be c. So c times 0 plus 1, or just c, equals 1. So that means c equals 1. Remember, right-hand side was 1, and left-hand side turns out to be c. So that means c has to be 1. So we found the value of c. And the second part says we have to find CDF, or capital F of x. So capital F of x, we know, is probability that x is capital X is less than or equal to x, and this is same as integral minus infinity to x f of t dt. So it doesn't matter. You can write capital F of x and therefore put x here and then integrate over t. Or you could say capital F of t and put t here and then integrate over x. Could have said f of x dx. So it doesn't matter. You put x here, t here, or t here, x here. Just make sure it's consistent with this one. If you put x here, then this should be capital F of x. And it should be x here. If you put t here, this should be t as well. And this should be capital F of t. And in that case here, you would have f of x dx. Now, what is the answer to this integral? Well, we have to look at the formula for small f. What is the formula for small f? It's c to power minus x for x bigger than 0, 0 for x less than 0. Now, if this x value is less than 0, so case 1, if x is less than 0, then capital F of x will be integral minus infinity to x of 0 dt. Let me show you on the real line. Before 0, small f is 0. So if x is somewhere here before 0, then I need to start with from minus infinity and move all the way to x. And small f is 0 there, and integral of 0 is 0. Now, case 2, if this number x is bigger than or equal to 0, then we can say that capital F of x is integral minus infinity to x f of t dt. And how can I proceed in this case? So again, if we look at the real line, this is 0, and then f is 0 before 0, and after 0, it's c, and c will turn out to be 1. So f of t will be just 1 times e to power minus t for t bigger than 0. So that means e to power minus t in this case. And in case 2 here, I'm assuming x is something bigger than 0. So x could be here. So if I start with minus infinity, start from minus infinity, I want to move all the way to x. So I can first move all the way to 0 and then 0 to x. So that means I can break down my integral to minus infinity to 0, f of t dt, plus integral 0 to x, e to power minus t dt. And then small f is 0 for t less than 0. So then this will be integral minus infinity to 0, 0 dt plus integral 0 to x, e to power minus t dt. Now this term is 0, integral 0 is 0. And then I just need an antiderivative of e to power minus t, which we just said a few minutes ago that it is minus e to power minus t. Then I need to calculate this between 0 to x. So then this becomes minus e to power minus x minus e to power 0. E to power 0 is 1. So the answer will be 1 minus e to power minus x. So this is the formula for capital F of x. Capital F of x is 1 minus e to power minus x. For x bigger than 0, bigger than or equal to 0. Therefore, we found the formula for capital F of x. Capital F of x equals 0 if x is less than 0, and 1 minus e to power minus x if x is bigger than or equal to 0. This is the formula for CDF. Question was asking us in part B to find the formula for CDF. Now in part C, we have to verify the properties of CDF in this example. So what were the properties of CDF? First of all, we were expecting that CDF is a continuous function if we have a continuous random variable. Here we have a continuous random variable. So that means capital F of X has to be continuous. So part C, first property, capital F of X must be continuous since we have a continuous random variable. And how can I verify this? Well, capital F of X contains two pieces. One piece is constant function 0, which is continuous everywhere. And another piece is an exponential function like this. We know exponential functions are continuous. So we can say that, note that y equals 0 and y equals 1 minus e to power minus x are both continuous functions. Continuous functions from Math 113. In Math 113, you saw that any constant function is continuous. E to the x is continuous, e to the minus x is, or e to the any polynomial is continuous, and 1 is continuous, the subtraction remains continuous. So these two functions are continuous. Now each piece is continuous, and if I want to check that the whole function is continuous, I need to check the continuity at the border point. So apart from border point, each piece is continuous. If I can check that the function is continuous at the border point, then that means function remains continuous everywhere. So next, check the continuity. At the border point, which is x equals 0. So what is the left limit and right limit at 0? So left limit, capital F of t approaches to 0 from left, means limit 0, t approaches 0 from left, and that is 0. And what about the right limit? Right limit, for right limit, I have to use this function here, the second piece, because this is the formula for x bigger than 0. So then this will be limit 1 minus e to power minus t approaches to 0 from right. So 1 minus e to power minus 0. E to power 0 is 1, so that's 1 minus 1, which is 0. So left limit and right limit both are 0. So we show that the left limit is same as right limit, same as 0, and 0 means f of 0. F of 0 is 1 minus e to power 0, which is also 0. So when can I say that the function is continuous at a given point? If the left limit and right limit and the output are all the same. So left limit, right limit, and f of 0 in this case are all 0. So that means all these three are equal. Therefore, f of t is continuous. F of x is continuous at x equals 0. That means f of x is continuous on minus infinity to infinity. We show that f of x is continuous at each piece and continuous at the border point, therefore continuous everywhere, meaning that continuous on minus infinity to infinity. So this was one condition we wanted to verify. Second condition of CDF, let's look at the second condition of CDF we mentioned earlier. Second condition, limit as t goes to infinity must be 1, t goes to minus infinity must be 0. So limit f of t goes to infinity. If t goes to infinity, I have to use the second formula, because for x bigger than 0, I have to use this formula. So 1 minus e to the power minus t goes to infinity. So this will be how much? If t goes to infinity, I will have 1 minus e to the power minus infinity. E to the power minus infinity is 0. So 1 minus 0, which is 1. And similarly, the left limit, for the left limit, I have to use, for t, limit t goes to minus infinity, I have to use the first formula here, because for x less than 0, I have to use this formula, and the function will be constant function 0. So I will have limit of constant function 0 limit 0 and this is 0. And so this was the second property. Third property, I need to check that capital F of t is an increasing function. Meaning that if a is less than equal to b, then f of a is less than equal to f of b. How can I check this? I have to consider different cases. See, I have two numbers, a and b, and I know that a is less than b. So case one, maybe both these numbers are before 0. Why am I comparing them with 0? Because at 0, the formula for the function changes. We're talking about capital F here. Capital F formula changes at 0. The formula changes at 0. So that's why I'm comparing a and b with 0. If a and b are both less than 0, then f of a and f of b are both 0, according to this formula. So case one, a is less than equal to b, less than equal to 0. Then we can say that capital F of a is 0, which is less than equal to capital F of b, which is also 0. Now, another case, if they're both bigger than 0, so let's say 0 is here, and a is here, b is here. So case 2, a less than equal to b, but they're both bigger than equal to 0. So then in this case, what will be f of a and f of b? So it seems that the screen was freeze for a few seconds. So for a, in the case 1, a less than equal to b less than equal to 0, f of a and f of b are both 0. Therefore, f of a is less than equal to f of b. Remember, our goal is to show that f of a is less than equal to f of b with the assumption that a is less than equal to b. And case 2, if a is less than or equal to b, but both bigger than or equal to 0, then what will be the formula for f of a and f of b? Again, remember that the formula for capital F is this. So if a and b are both bigger than or equal to 0, for both of them, I have to use this formula. So f of a would be 1 minus e to power minus a, and f of b would be 1 minus e to power minus b. Then f of a will be 1 minus e to power minus a, and f of b will be 1 minus e to power minus b. Now, how can I compare these two numbers? Note that we're assuming that a is less than or equal to b. So if I multiply both sides with minus 1, I'll get minus a bigger than or equal to minus b. And this means e to power minus a bigger than or equal to e to power minus b. Because remember that since e to power x is increasing. E to power x itself is an increasing function. So if you have two inputs, one bigger than the other one, e to that power, e to first power is bigger than e to the second power. And if I multiply both sides with minus 1, because here, look at here, I have minus e to power minus a and minus e to power minus b. Right now, I have e to power minus a and e to power minus b. So if I multiply both sides with minus 1, I'll get minus e to power minus a less than equal to minus e to power minus b. And if I add with 1 both sides, I'll get 1 minus e to power minus a less than equal to 1 minus e to power minus b. And this is my capital F of a. This is my capital F of b. So we showed capital F of a less than equal to capital F of b in this case. And finally, the last case, because remember in case 1, I assume I have two numbers, both less than 0. Case 2, both bigger than 0. So the last case will be the case where one of them is less than 0 and one of them is bigger than 0. So the smaller one, I'm calling it A. So A in case 3, A would be less than 0 and B will be bigger than 0. So 0 is here, and let's say A is here, B is here. So 0 less than equal to A less than equal to A less than equal to 0 less than equal to B. So in this case, then we can say that f of a, for a less than 0, what is capital F of a? Capital F of x, for x less than 0, we said it's 0. So capital F of a will be 0, and b is bigger than 0, so capital F of b will be 1 minus e to power minus b. So capital F of a will be 0, which will be less than equal to 1 minus e to power minus b, which is capital F of b. So I just need to verify this inequality. If I can verify that 0 is less than equal to this number, then I'm done, because then this is f of a and this will be f of b. Why 0 is less than this number? If I call this one, let's say 2 star. So justification for 2 star is b. What do I know about b? I know that b is bigger than 0. So that means minus b will be less than 0. So e to power minus b will be less than e to power 0, which is 1. Remember, we said exponential e to the x is increasing function. So if you have two numbers, first less than second, e to first number will be less than e to the second number. So e to power minus b less than e to power 0. And this means 1 minus e to power minus b. If I take this term to the other side, becomes 1 minus e to power minus b bigger than or equal to 0. Which is what we were saying here, 1 minus e to the power minus b bigger than or equal to 0. So we assumed a is less than b, and we considered three cases. In each case, we show that f of a must be less than f of b. Therefore, based on cases 1, 2, 3 above, we conclude that if a is less than or equal to b, then capital F of a is less than or equal to capital F of b. And finally, the fourth property of CDF is that derivative of CDF should be PDF as long as PDF is continuous. Well, PDF is continuous on which intervals? Look at the formula for PDF. C turned out to be 1. So on open intervals 0 to infinity, PDF is continuous, is e to power minus x, which is continuous. And on minus infinity to 0, PDF is constant function 0, which is continuous. So these are the intervals that I can use in order to check whether derivative of CDF is PDF. So on minus infinity to 0, f of x is 0, which is a continuous function. And derivative of CDF, what is CDF for x less than 0? For x less than 0, the formula for CDF is 0. For x bigger than 0, the formula for CDF is 1 minus e to power minus x. So for x less than 0, the formula for CDF is 0. D to dx of 0 is 0, which is same as small f. And on 0 to infinity, small f of x was e to power minus x. Again, a continuous function. And what is derivative of CDF? It will be derivative of, what was the formula for CDF for x bigger than 0? If you remember, it was 1 minus e to power minus x. Derivative of this function is e to power minus x, which is same as PDF. So we verified all the 4 properties of CDF in this example.